Hello everyone, so welcome back. So hope you have been finding my videos useful and day by day your concepts of physics are getting strengthened. So in this video we will learn about geometrical optics. So I plan to cover the theory of geometrical optics in two videos. In the first video, which is the current video, I will cover reflection and I will apply the concept of reflection to mirror. In the second video, I will cover refraction and I will apply the concept of refraction to lens. So, so let's get started with reflection. Now let's understand linear and spherical mirror. So this is a linear mirror. So we get a linear mirror by taking a piece of transparent glass and we make one side of the glass opaque by silver painting it. So let's say we have an object O in front of the linear mirror. The object emits light towards the mirror. The light after hitting the mirror gets reflected and it reaches an observer, the eyes of an observer standing on the ground. For the observer, it appears as if the light has been coming from an object or an image O dash, which is behind the mirror. Now, for in case of linear mirror, the distance of the image from the mirror behind of course, the mirror is equal to the distance of the object from the mirror. Now, as I have told, the light which goes from the object and hits the mirror is called incident ray. The light which gets reflected is called reflected ray. The Now let's say this is the point where the incident ray hits the mirror. If we draw a perpendicular at this point to the mirror, then the angle which the incident ray makes with the perpendicular is called angle of incidence, and the angle which the reflected ray makes with this perpendicular is called angle of reflection. For a linear mirror, angle of incidence is equal to angle of reflection. Now let's understand spherical mirror. So how do we make a spherical mirror? We take a hollow piece of sphere which is made up of transparent glass. We cut the sphere into two equal halves, and we paint, paint the outer surface of one of the half with opaque silver paint, and we paint the inner surface of the other half with opaque silver paint. Now the mirror, whose outer surface is opaque, is called concave mirror, and the mirror whose inner surface is opaque is called convex mirror. So for a concave mirror, reflection will happen at the inner surface of the mirror. For a convex mirror, reflection will happen at the outer surface of the mirror. The center of the mirror is denoted by R. The midpoint of the mirror is denoted by point P, which is called the pole of the mirror. The line joining point R with point P is called the principal axis of the mirror. Now let's say we have one concave mirror and one convex mirror. And let's say we have a parallel beam of light which hits the concave mirror very close to the principal axis. So after hitting the concave mirror, the reflected beam crossed the principal axis at a point which is denoted by F. This point F is called the focus of the mirror. Similarly, for a convex mirror, the parallel beam of light after hitting the mirror will diverge. If we protrude if we project the divergent beam behind the mirror, we'll find that they cross the principal axis again at a point which is called F, and which is again the focus of the mirror. The distance between the point F and point P is called focal length. Now let's derive the mathematical equation of a spherical mirror. So let's say we have an object O which is situated at a distance of u from the spherical mirror, from concave spherical mirror. Let's say a ray of light from the object O hits the concave spherical mirror at point A, and the reflected ray crosses the principal axis at point I. Okay. Please note that I is not the focus because the incident ray is not parallel to the principal axis. Please also note that C is the center of the mirror. So AC is normal to the mirror. Hence, by the geometrical property of the mirror, the angle of incidence, which is angle OAC, is equal to the angle of reflection, which is angle CAI, which is equal to theta. So let's denote angle AOP as alpha, angle ACP as beta, and angle AIP as gamma. Now if we consider angle OAC, beta will be equal to theta plus alpha. Beta is equal to theta plus alpha by the property of triangle. If we consider angle OAI, gamma is equal to 2 theta plus alpha. If we solve these two equations, I mean, if we from these two equations, we get 2 beta is equal to alpha plus gamma. And if we assume that this point A, where the incident ray hits the mirror, is very close to the pole of the mirror, then the angles alpha, beta, and gamma are very small. And for very small angles, as I mentioned in my first video on in mathematics and physics, we can write alpha as AP by OP, beta as AP by PC, and gamma as AP by PI. If we put these values in this equation, we get 1 by PO plus 1 by PI is equal to 2 by PC. Now, what is the value of PO, PI, and PC? Here, we have to follow a sign convention when we enter the value of PO, PI, and PC to ensure consistency across spherical mirrors if we encounter in our analysis. Now, there are two rules of in the sign convention. The first rule is the direction of the incident ray is considered to be the positive direction, and the direction opposite to the incident ray is considered to be the negative direction. The second rule is that all distances should be measured from the pole as the starting point. So if we apply these rules for PO, what will be the value of PO? So first of all, PO, which is the distance of object from pole. So for PO, we are going, I mean, in the direction opposite to the direction of the incident ray. So the value of PO is negative. And what is the val? And what is PO? In magnitude, it is U. So PO will be minus U. Similarly, PI will be minus V, where V is the distance, the magnitude of the distance of the image from the pole, and PC will be R minus R, where R is the magnitude of the radius. So if we put these values in this equation, we get 1 by U plus 1 by V is equal to 2 by R. This is the equation of the spherical mirror. Now let's say we have a ray of light coming from a far object. So from a far object, we can consider the ray of light to be parallel to the principal axis. So when the parallel ray of light hits the spherical mirror or a concave spherical mirror, the reflected ray will pass through focus. So if we apply this equation, the equation which we derived earlier in this case, we will have U is equal to infinity because the object is at a very far distance from the mirror. V will be equal to F, or rather I should have here V will be equal to minus F. And so if we apply if we put values in the equation of the mirror, we'll have minus 1 by F is equal to minus 2 by, so F is equal to R by 2. So focal length is equal to half of the radius. So if we put the value of F in the first equation, we get 1 by U plus 1 by V is equal to 1 by F. So this is another form of the same equation. So now let's learn about magnification. So let's say we have an extended object AB in front of a concave spherical mirror, and let's say light from the tip B of the object hits the mirror and gets reflected. Similarly, one ray of light will hit the pole of the mirror and get reflected. So we will get the image of point B as B dash on the mirror, and for A we will get the image as A dash in front of the mirror. So for the extended object AB, we will have A dash B dash as the image. Now we define magnification as magnification ratio as height of image divided by height of object. Okay. So now if we consider triangle ABO and triangle A dash B dash O, find that these two triangles are similar. Let's see how. So angle BAO is 90 degree, and so is angle B dash A dash. Okay. Now BO is the incident ray, and B dash O is the reflected ray, and AO is the normal about which the reflection is happening. So by law of reflection, angle of incidence is equal to angle of reflection. Hence angle BOA is equal to angle B dash O A dash. Hence these two angles are also equal. So the third angle, which is A dash B dash O, will be also equal to angle ABO. Hence these two triangles are similar. Now, by the property of similar triangles, we have A dash B dash divided by AB is equal to um, A dash O divided by AO. Okay. Now let's apply sign convention and fill in the values of A dash, B dash and these variables. So what is A dash, B dash? A dash, B dash is nothing but the height of image, and the image as you see is below the this axis. So we will add negative sign to it. So let me call this minus height of image. AB is the object, and it is on the positive side of axis. So let me call it HO is equal to A dash O. So A dash O is A dash O, as we can see, is V. And what is what will be the sign of V? The sign of V will be negative, because positive direction is this one, along the direction of incident ray. So it will be minus V, and AO will be U, again negative direction, so minus U. Hence HI, which is height of image divided by height of object, is equal to minus V by U, which is minus of image distance by object distance. So this is how we define magnification of an object in case of mirror. So that's all I have in this video. In the next video, we will learn about refraction, and we'll use refraction concepts to further learn about lens, and we will derive the lens maker's formula. So thank you. Thanks for watching.